Hello everyone. So we'll start with peptization. We were doing the methods of preparation of colloidal sole, and the last method discussed was peptization. So peptization is the process of conversion of freshly prepared precipitates by addition of a suitable electrolyte in the presence of dispersion medium. So freshly prepared particles to colloidal particles with the addition of electrolyte in dispersion medium presence. Now, the examples of soles obtained by peptization. The first example is ferric chloride sole, which is obtained by the addition of ferric chloride in freshly prepared ferric hydroxide precipitates. And the other example is the addition of silver nitrate or potassium iodide in silver iodide precipitates to get the sole of silver iodide. Now, what is the cause of peptization? Why the precipitates are converting to colloidal size by the addition of electrolyte. So here the reason is preferential adsorption. So preferential adsorption of the ion, which is common to the precipitates from the electrolyte, is adsorbed at the surface of the precipitates molecules and create electrostatic repulsions in between those particles and converting them to colloidal range. So this is how it works. So like here in this case, if in case of silver iodide, we add potassium iodide. So silver iodide, addition of potassium iodide in silver iodide gives negative sole because the particle which is common to the silver iodide is iodine. So in this case, iodine is going to be adsorbed at the surface of silver iodide precipitates. Whereas if we use silver nitrate in silver iodide, so in that case, positive sole is obtained. So positive sole particles will be obtained because silver is common to the silver iodide from the silver nitrate. So it is going to be adsorbed at the surface. So this is the preferential adsorption of the common ion, which gives the charge. Now, next is the method of purification of colloidal solutions. So, when we prepare the colloidal solutions, we use electrolytes, and those electrolytes are acting as crystalloids impurities. And to remove those impurities, we have some methods which make the colloidal solutions pure up to a certain level. So the first method is dialysis. The first method is dialysis, and in this technique, the colloidal solution is kept inside a parchment membrane or animal membrane and is placed in the dispersion medium, where the dispersion medium is entering from the one side and leaving the container from the other side. So during this process, the animal membrane is uh, uh, selectively allows the crystalloids particles to move out from them and not allowing the uh, colloidal particles to go out. So with the passage of time, the dispersion medium takes away with them all the crystalloids from the sample, and the sample becomes pure. So then next is electrodialysis. The same dialysis process can be fastened with the use of electrolytes, as the colloidal particles and the crystalloid particles are charged because they are the part of electrolyte, so they can be removed faster with the application of electrodes in the dialysis process. Then next method is ultrafiltration. The ultrafiltration is the method where ultrafilter paper is used instead of normal filter paper. And now, what is the ultrafiltration filter paper? The ultrafilter paper is the filter paper which is treated by the colloidal or gelatin solution, which makes the pores of the filter paper narrow or small, and by doing so, uh, the crystalloid particles can move through the filter paper, and colloidal particles will not move through that filter paper. So the ultrafiltration method can be used. And this colloidal solution is the 4% solution of nitrocellulose in alcohol or ether. In alcohol and ether, 4% nitrocellulose solution in alcohol and ether. So if this solution, this mixture is applied on the normal filter paper, its pore size becomes small, and that filter paper is known as ultra filter paper, and it will not allow the colloidal particles to move through it. So these are the processes by which we can uh, uh, define the colloidal solutions. Next is the properties of the colloidal solution. So first we'll discuss physical properties. They are heterogeneous in nature. They are very stable. They can be filtered with the help of animal membrane or ultrafilter paper. They are translucent in nature. They are not clear. They are translucent. These are the physical properties. Next is the qualitative property. Now, as the colloidal particles are of bigger size, so they have large molecular masses as compared to the true solution particles, which makes the colloidal uh, properties value very small, which makes the colloidal uh, qualitative properties value very small, because the qualitative properties are inversely proportional to the molar mass. So here the mass of the colloidal particle is large as compared to the true solution particles. So the values of qualitative properties are very small. Only measurable value of a qualitative property is for osmotic pressure, right? So osmotic pressure is used to determine the molar mass of colloidal solutions. Then mechanical properties includes the Brownian moment. The Brownian moment is the zigzag movement shown by the colloidal particles in the uh, colloidal solution when the dispersed phase is suspended in the dispersion medium. So they show zigzag motion, which is a continuous motion, and due to this motion, the stability of the colloid is justified. Now, why this motion is there? Because when the particles are moving, they have imbalanced forces of attractions and repulsions on them of the dispersion medium. Those created imbalanced forces on the colloidal particles, which result in the movement of the colloidal particles. Whereas in case of true solutions, this thing is not happening, because there the particle size is very small, and the motion is not captured. Next is the optical properties. Optical property involves Tyndall effect. It means when we pass the light through the colloidal solution, the path of the light is illuminated, and that illuminated path is known as Tyndall cone, and the phenomena is known as Tyndall effect. Next is electrical properties. First of all, electrical properties involves charge on the colloidal particles, and this charge is the reason for stability of the colloidal particles. Now, colloidal particles always carry the electric charge on them. So they all contain same charge. Due to that, they have some electrostatic repulsions. So those repulsions are responsible for the stability. So generally, the soles are of two types: negatively and positively charged soles. So in general, the positively charged soles are hydrated metal oxide soles, basic dyestuffs, hemoglobin, whereas negatively dye are metal fights, metal soles, acid dyestuff soles, sole of starch, gum, gelatin, all are negative in nature. Now, what is the origin of electrical charge on the colloidal particle? So there are different theories which justify this. The first is the frictional electrification caused by the mutual rubbing of the colloidal particles with the dispersion medium particle. So this is the first theory. Next theory is the electron capture by the particles from the air during electrode dispersion method, which is Briggs arc method. So first is the mutual rubbing, and the second is the electron capture from the air. And the third, which is most important and most acceptable theory, is preferential adsorption of ions from the solution. So this is the common ion which is going to be adsorbed on the colloidal particles. Like same example, silver iodide sole with the help of silver nitrate, so and silver iodide. So the first case where the potassium iodide is added to the silver iodide. So iodine is going to be adsorbed because iodine is common to the silver iodide. Negatively charged soul particles are formed. So in same case, if we have to produce silver iodide soul, and in this case we are adding silver nitrate to the potassium iodide. In the first case, we are adding potassium iodide to the silver nitrate, and potassium iodide is going to be slightly extra, slightly in excess as compared to the silver nitrate. So excess is iodide ion, which are common to the silver iodide. So here we are adding silver nitrate to the silver iodide. So we'll add till it is slightly excess in silver ions. So which ions are in excess now? Silver. So they are going to be absorbed. So they are common to the colloidal particles. So this is how they get the charge by preferential adsorption. Now next method is dissociation of molecules followed by aggregation of ions. So this case is for the associated colloids like soap, micelles, where the micelles are formed. So dissociation of molecules, then aggregation. Micelle formation is the example, and in this case, the particles having charge are, are placed outside. The molecules are placed in the same direction, and hence they get charge on the surface. So it depends which charge is there is on the basically on the nature of the molecule we are using or the sample we are using. Then the next method is dissociation of molecular electrolytes adsorbed on the surface of particle. So dissociation of molecular electrolytes. So this method is, for example, we are preparing arsenious sulfide sold by using a arsenious oxide and hydrogen sulfide. This is double decomposition method. So in this method, the H2S molecules gets adsorbed at the surface of this particles of sulfide, arsenious sulfide basically. So H ions are lost during the process and the sulfide ions are present over the surface. So dissociation of molecular electrolytes. So which molecular electrolyte? H2S on the surface of sulfide, that is arsenious sulfide, right? So dissociation of molecular electrolyte. So dissociation of H2S into H ions and S2 negative. So negative will remain there and the H ion lost. In case of ferric hydroxide soul, the particles are positively due to the self-dissociation, and OH ions are lost to the solution, giving the positive charge to the particle. So this is the example we discussed earlier, ferric hydroxide soul. So in case we are using ferric chloride in excess, then it will become positively charged, and ferric hydroxide will be negative if it undergo the self-dissociation. It gain positive due to because ferric chloride is used, and self-dissociation causes ferric ions excess, and those ions makes it positive. Right. Next topic is zeta potential. So preferential adsorption of ions is the basic theory which is accepted at large for the explanation of the reason behind the region of the charge on the soul particles. So basically here we have the soul particles, and the common particle to them is iodide ion if we are using potassium iodide and silver iodide. So case we are using potassium iodide in excess. So the first layer formed is fixed layer, and the other layer is the mobile layer, which is diffused, diffused or mobile to the first layer in comparison to the first layer. So alternatively, this picture can be represented in this manner also. So the double layer formed having the opposite charges is called Helmholtz electrical double layer. So there is a obviously if the charges are opposite in this layer, so they have a potential difference. There is a potential difference in between the two layers, and this potential difference is known as zeta potential or electrokinetic potential. Next, second electrical property. The first electrical property is the charge on the colloidal particles, and the second electrical property is the electrophoresis or cataphoresis. As the particles are charged, so when they are placed in a electric field, so the particles always moves towards the opposite electrode. So negative colloidal particles will accumulated at the positive electrode when an electric field is applied, and this process is known as electrophoresis. Next is the coagulation. Coagulation, fluctuation, precipitation, same terms. So it is opposite to the peptization. So in peptization, the precipitates are converted to colloidal particles, whereas in case of coagulation, the colloidal particles aggregates together to form precipitates. Again, by the use of electrolytes. So electrolytes remove the charge on the particles, and due to the removal of charge, they come close to each other and they join to each other and form aggregates, and uh, coagulation will happen. Now, the electrolyte amount in millimoles, minimum electrolyte amount in millimoles, which is required to coagulate a liter of colloidal solution, is known as coagulation value, fluctuation value, or precipitation value. The electrolyte which have low fluctuation value or coagulation value is more effective because its small amount is more effective. One rule is there, Hadley-Stew's rules, which states that greater is the valency of the coagulating or the fluctuating ion, greater is its power to coagulation of coagulation. Like out of Al3, aluminium 3, barium or sodium ion, aluminium have more charge on it, so it is more effective than the sodium. Same here. So PO4 3 negative is more effective than SO4 2 negative, and Cl4 is least. Next is electrophoresis for coagulation. So if we pass the current through the colloidal solution, so the oppositely charged particle attract towards opposite electrode and accumulated there. So this will create the precipitation. So mutual precipitation. So if we add two oppositely charged, opposite type of colloidal particles, colloidal solutions together, they utilize their charges, and then the coagulation will happen. Prolonged dialysis. If we continue the dialysis process by stopping the fresh dispersion medium, then it will remove all the dispersion medium from the colloidal particles, and we'll get the precipitate of the colloidal particles. By heating or cooling, like in case of milk is an colloidal solution. We heat it, we get the cream over it. The precipitates of its particles is colloidal particles, and by cooling, so if we kept the milk in fridge, we'll obtain the colloidal particles precipitation over it. So these are the methods by which coagulation can be obtained. Next is the protective action of lyophilic colloids. So lyophobic colloids are unstable and can be precipitated easily. So these can be protected by the by addition of lyophilic particles in them. So it is assumed, it is believed that the lyophilic particles dissolve themselves on the lyophobic particles and make them stable. So, but this theory is not acceptable. But this is the only theory. This is not acceptable because the colloidal range particles are almost same. So, how can the lyophilic particles can be absorbed with the lyophobic particle? But it is like this only. So, this is the only one theory which justifies the protection of lyophobic by the lyophilic particles. Next is the emulsions. So emulsions are the colloidal solutions where both dispersion medium and dispersed phase are liquids. So generally, if the two liquids are not stable with each other, then emulsifying agents are used. Like in case of oil in water, the emulsifying agent soap can be used. So it is the same concept like micelle formation by grabbing the oil particle in between them. So hydrophobic part towards oil and hydrophilic towards to water. So this is the role of emulsifier soap, which keep the two different type of liquids together. Right. there are two types of emulsions, oil in water and water in oil. So oil in water, oil is dispersion medium, water in oil, water is dispersion medium. Oil in water is example milk, cod liver oil is example of water in oil, butter, water in oil, cold cream. So emulsion shows all the properties of colloidal solutions, and we can get the constituents of emulsion back by demulsification process. And demulsification process is the coagulation process, like by centrifugation of milk, by heating, by addition of electrolyte like nimbu, like lemon. If we add 3-4 drops of lemon in milk, it coagulates and converted to cheese. Uh, so demulsification process or coagulation process. So application of colloids in daily life. So medicines like uh, eye lotions of silver sol, argyrol is a colloidal solution. Kala Azar treatment with colloidal antimony. Milk of magnesia using as an antacid is colloidal solution. So food articles like butter, milk, ice cream are the colloidal particles. Fog, mist, clouds are all our colloidal particles. Formation of delta. So delta is a place which is above the level of sea, where the two rivers are falling into the sea, the land level rises up. So this happens due to the mutual precipitation, mutual coagulation of the particles, colloidal solution of two rivers. So river water is considered as colloidal solution, and if the two rivers are combining with each other, they mutually precipitate their colloidal solutions, and the precipitation will occur, and this precipitation results into the formation of delta. Blue color of sky and even the sea is due to the Tyndall effect of seawater given by the seawater and by the dust in air. So blood is also a colloidal solution. So this is all about your chapter number 5, surface chemistry. So I will send you some questions on it in the next session. Right. Thank you and bye for now.